Hello students, today we're going to discuss the physical properties of haloalkanes and haloarenes. Before discussing the physical properties, just make a habit that what is the intermolecular force which affects their physical properties. So as we have seen earlier in the beginning, haloalkane and in haloarenes, CCl bond is polar. So definitely we can predict the intermolecular force of attraction. The intermolecular force of attraction is dipole-dipole. And when there is a dipole-dipole, then there is addition of van der Waals force due to size, due to molecular mass. So the intermolecular forces operating in haloalkanes and haloarenes is dipole-dipole and van der Waals force. First, we will discuss the physical state. Lower members like CH3Cl, CH3Br, C2H5, etc. are gases at room temperature, but higher members are liquid or solids. Definitely, you can predict that why higher members are liquids and solids. It's all um, as the size of the molecule increases, the magnitude of van der Waals force also increases, and molecule come closer. And when molecule come closer, the gases converted into liquids and liquid into solids. The important aspect in the physical properties of haloalkanes and haloarenes is boiling point and melting point. Basically, we'll concentrate on boiling point. I have listed some points. The first thing is boiling point is compared uh, with the parent of haloalkanes or haloarenes. Who is the parent? Parent is the alkanes. Okay, aliphatic compound. So as you know that alkanes are non-polar, whereas haloalkanes and haloarenes, they are polar. So what is written here? Higher than corresponding alkanes means the boiling and melting point of haloalkanes is higher than the alkanes of comparable molecular mass. Okay. Then what is the reason? The reason I have mentioned in the blue. The reason I have mentioned with the blue pen, due to greater polarity and molecular size. I repeat, due to greater polarity and molecular size. You can say molecular mass also, because halogen, the mass is more than hydrogen, okay, or carbon. So therefore, you can say due to greater polarity, and the magnitude of dipole-dipole or van der Waals force is more. So if the magnitude of dipole-dipole or van der Waals is more, okay, it means the molecule remain closer, then that is reflected in their properties. Second point, for the same alkyl group, you see, if the alkyl portion is same, the order of boiling point is RF is less than RCl is less than RBr is less than RI. It means if you move on from fluorine to iodine, you know that there is an increase in the size and mass of halogen. Okay, definitely the magnitude of van der Waals force increases. Next, for the same halogen atom, now the alkyl part is changing now. With the increase in size of alkyl group, boiling point also increases because of the same reason. So here you see methyl chloride, ethyl chloride, and then propyl chloride. So when you move from methyl to propyl, what get increases? The size, the molar mass. So definitely the magnitude of van der Waals force also increases. Now this is important. For the isomeric haloalkanes, the boiling point decreases with the increase in branching. So I have taken this as an example, N-butyl chloride. This is secondary butyl chloride. This is isobutyl chloride. This is tertiary butyl chloride. So when you move from N-butyl chloride to tertiary butyl chloride, you see the branching get increases. And with the increase in branching, the surface area of the molecule decreases. And when surface area of the molecule decreases, the magnitude of van der Waals force decreases. And this is the reason why, with the increase in branching, the boiling point of different isomeric haloalkanes decreases. Now, boiling point of alkyl halide increases with the number of halogen atoms. This is expected as you increase the number of halogen atoms, the boiling point increases with the increase in magnitude of van der Waals force. So these are the things which is related with boiling point. The next property. First, we have seen physical state, second, boiling point, and the third physical property is solubility. The haloalkanes are only slightly soluble in water. The haloalkanes are only slightly soluble in water. This is the solubility of haloalkanes in polar solvent, because water is a polar solvent. The reason is mentioned here. Energy is required to overcome the attraction between the haloalkane molecules and to break the hydrogen bond between water molecules. Okay, so you need energy to break the previous bonding present in the haloalkanes and water. And you know that in water, hydrogen bonding is present. Less energy is released when a new attraction are set up. It means when a new attraction, when both are mixed, the new attraction is set up between alkyl halide and water. So less energy is released. Why? Because most of the alkyl halide not able to form hydrogen bonding with water molecule. Although they are polar, but they are not able to form hydrogen bonding. You know the criteria of hydrogen bonding. Okay, except few fluoride, which is not mentioned here, because we are discussing the general properties and we are discussing the general things. So in most of the cases, we find that alkyl halide not able to form hydrogen bonding, and therefore it is written less energy is released when new attractions are set up between the haloalkanes and the water molecule, as these are not as strong as original hydrogen bond in water. Okay, so this is the reason why uh, haloalkanes or haloarenes are insoluble in water, but they are highly soluble in organic solvents like benzene, carbon tetrachloride, carbon disulfide. Okay, then fourth point, I am mentioning it separately, the boiling and melting point of haloarenes. There is nothing special except one. The boiling point of isomeric dihalobenzene are almost same. So boiling point of isomeric dihalobenzene is almost same. So when you make a dihalobenzene like this, okay, this is ortho, and this one is meta, and this one is para. This is para. So their boiling points are almost same. But what is special thing here? Melting point of para isomer. This is the para isomer. I repeat, melting point of para isomer is more as compared to ortho and meta isomer. Is more as compared to these two isomer. The reason you know that para isomer is symmetrical. We have discussed earlier also, this isomer is symmetrical. Okay, and when the molecule is symmetrical, it fits, because melting point is for the solid. So We have to see that how in crystal the molecule is fitting. So it fits in the crystal lattice well. I repeat, it fits in the crystal lattice well. Okay, it fits in the crystal lattice, you can say, better. And this is the reason it is more energy is required to separate that, and the melting point would be more. So this is about the physical properties of haloalkane and haloarenes. And as I said earlier, I'll be giving you as assignment later on based on different topics. Okay, so